Where are we? Okay, so probability, yeah, so the topic for today. Yeah, so this, as I mentioned, yeah, we've tried to put the probability stuff that's needed for the course in this module here. So first of all is the Gaussian distributions. Yeah, so this is kind of from statistics, and there's this central limit theorem that says that if you add up a large number of independent variables, you tend to get a Gaussian distribution, and this is what they look like with different means and standard deviations. So this is in one dimension, and this is in multiple dimensions. So there's a slight thing with the notation is that a little sigma with the multiple dimensions, the capital sigma is used for the variance, which is a matrix. In one dimension, the small sigma is used for the standard deviation, which is the square root of the variance. So that's just like a notational convention. Yeah, so this is like, yeah, the Gaussian distributions. And then we've got conditional probability. So this is where, yeah, the probability of A given B is the probability of A intersection B divided by the probability of B. And then this leads to Bayes' rule, where we get the probability of A given B is equal to the probability of B given A times the probability of A divided by probability of B. So often this is used to find the probability of a cause given an effect when we know the probability of effects given the cause. So here's like an example. You sometimes see examples with medical diagnosis. I think in this exercise today. Yeah, so you can use this in areas where, like, yeah, here you're pulling balls out of a bag and you have to figure out what's the likelihood of each bag. I think, I'm not sure if there's, in the video, there may be a medical diagnosis example, but here's another example where light bulbs are coming out of two different factories, and you have to guess the probability of it, whether it came out of factory A or B. So these are sort of standard applications of Bayes' rule. And then we have yeah, entropy and Huffman coding. So the I try to explain this. I try to give the discrete case first and then the continuous case. And I try to explain in terms of coding theory, just to kind of make it a bit more tangible. Yeah, so if you have a discrete probability distribution, this is the formula for entropy, the sum of pi minus log of pi. So in computer science, in this context, we usually take log base 2. Otherwise, it'd be multiplied by some constant. The pi's, because their probabilities have to add up to 1, so this is like a weighted average. And because pi is a number between 0 and 1, the negative log is positive. Yeah, so we can interpret this in certain cases with the Huffman coding. We can interpret this as the average number of bits that we need to send to encode one symbol. So these are just some examples. This is if you've got two symbols that are equally likely, then you need 1 bit. If you've got 3 symbols, but one is twice as likely as the other 2, on average, you need 1.5 bits, because half the time you need 1 bit and the other half you need 2 bits. And then if the probabilities don't give you this sort of neat divide like this, then in order to achieve this, you have to use a block encoding and this kind of thing. But basically, this entropy tells you the average number of bits, in an efficient code. And then we have this concept of the KL divergence, which measures how similar one distribution is to another. So it's much like a distance, but it's not symmetric. The KL divergence from P to Q and from Q to P may not be the same. So that's why we use the word divergence rather than distance. And in the discrete case, we can interpret this again in terms of coding theory. It's the number of extra bits that we would need to transmit if we designed a code that's optimal for Q, but then it turns out that the symbols are instead chosen from the distribution of P. And it's always positive. This number's always positive or 0, and if P and Q are equal, it's 0. And then, right, so that's the discrete case. Now then, but we're also interested in the continuous case. So with the continuous case, it becomes a little bit more less tangible, because there's if you think about it in terms of coding theory, you can interpret it in terms of coding theory, but the thing is, you're trying to send a continuous number, so you have to decide what resolution, what precision you're going to send. You're going to send it to 2 decimal places or 3 decimal places, and that kind of thing. So it becomes a little bit more complicated, and but it's the same. The formula is the same. Instead of the sum, it becomes an integral. So it's the average value of the log of probability, and here it's the average value of the difference of the 2 logs. Okay, Hugh's asking, do Huffman coding schemes share the same properties as a BST? Yes, Huffman tree can be seen as a BST. And I mean, the Huffman tree is not unique. You'll see I could have had B and C for this one here, I could have had B and C in the left branch and A in the right branch. There's usually multiple. Here I could have had A on the left and B on the right. So there's always multiple different Huffman trees that you can use to encode these things. I've just sort of created these so that the symbols are in alphabetical order, but there's multiple different Huffman trees, but they would all have the same efficiency. Ching Dung is asking whether there's an example for something. I don't know, when you, what is it? Maybe you could be more specific what you're looking for an example of. I follow along with the background, right? So, okay, so James is asking, can't picture the goal of what we're trying to do with it. Okay, so maybe I just, yeah, I sort of, this is, I've split this up as two different modules, but the material for tomorrow, we discuss certain variations on backpropagation, and I try to give like, where possible, like an intuitive explanation and also some mathematical explanation. So cross entropy, right, so we'll be using maximum likelihood to derive this sum squared error and cross entropy. So this is where we're using, yeah, we'll use the Gaussian distribution here and the conditional probability. And then when we get to weight decay and momentum, so for weight decay, we'll be using Bayes' rule. Okay, so I've tried to kind of, I feel like it's better to kind of present the mathematics in one module and then the application of it to neural networks in the second module. And so if you're looking for, yeah, if you're looking for like the application of this, just have a look through tomorrow's material and then we can discuss it tomorrow if you have any questions. Now the other stuff, so the multivariate, okay, so then when we get to, so that covers this part. Now when we get to the KL divergence, so the KL divergence, the main place, there actually are a number of deep learning algorithms which use KL divergence, but the place where we're going to see it mainly in this course is the variational autoencoder. It'll be in the last week or the second, week 9, the second last week. Is where we'll see this, but it's important to, this is an important concept because like it does come up in some reinforcement learning algorithms as well, although we might not be covering those in detail. And perhaps I should warn you, there's where is it? When we do get to the variational autoencoders, there'll be a little bit more math when we get to the variational autoencoders. Just show actually this. So this is the formula for KL divergence. Now in the specific case where the two distributions are both Gaussian, there's specific formulas for the KL divergence in that case based on the mean and variance of the Gaussian distribution. So there's some extra formulas. These formulas I have held back into the place where we're actually use it in an application because I thought it was a little bit much to include this at this stage. So yeah, that'll be coming up in week 9, but for the moment we're just kind of introducing this concept of this KL divergence, and I've tried to give an explanation here which is based on this blog I took these pictures from the blog, obviously, that, you know, in some situations, we try to minimize the forward KL divergence and sometimes the reverse KL divergence. And I've tried to sort of explain the difference between the two. Which of these is okay? The 4. Okay, up to week 5 is visible to you guys now. It's always a bit of a struggle to know what to put in the beginning and what to put into the context, because some students say that they want to have the math all at the beginning because they want to know right up front what math is being assumed. So that's why I put tried to collect it into that one module. But this is if you want to see an example of something that's a very good approximation to a Gaussian distribution. Yeah, we sort of talk about this a little bit in week 4 when we get to weight initialization. So this coin tossing example, you know, if you toss a coin 1,000 times or 10,000 times, then and you measure the number of heads, then that distribution, because of the central limit theorem, that distribution will be very, very, very close to a Gaussian distribution. And you can figure out the mean and the variance of that Gaussian distribution. If you toss one coin, the mean is 0, the mean of the number of heads is 0.5 and the variance is 0.25. And if you toss it n times, then you multiply both the mean and the variance by n, which means the standard deviation gets multiplied by square root of n. So if you're the kind of person who likes to see the application of something rather than just seeing it first, you can go and have a bit of a look at this example in 4B. This is where this kind of Gaussian distributions are used. So yeah, that's interesting. Yeah. Anyway, that's yeah, like I say, I mean, I could have put the coin tossing example in here, but then by the time we got to week 4, you might have forgotten it. Yeah, I think we talked about this last week. We didn't include a mathematics refresher here, but we talked about how some other courses had some links to Khan Academy and stuff. Like, if you want, I can try to find a some videos that discuss this this probability stuff. Yeah, and put some links to it. But I would have thought, I mean, this conditional probability, I think most people should have done this in high school. Yeah, but it's sometimes it's good to refresh our memories. Oh, sorry, that was probability. Yeah, let me go. So there's also like there's also this generalization and overfitting. So this is something that would be familiar to you guys from the machine learning course. Sorry, anyone who's done the machine learning course will be familiar with this already, but this is sort of what we need for our purposes. So we divide learning into 3, the supervised learning, and then most of the course will be unsupervised learning, and then in the last few weeks we'll do reinforcement learning and unsupervised learning. Supervised learning, we have a training set and a test set, and the aim is to get train something that will perform well on both the training set and the test set. So if we want to avoid the situation where it performs well on the training set but not on the test set, that's known as overfitting. Whereas if it performs well on the test set as well, we say that it has good generalization. And yeah, we have to take account of noise in the training data and outliers. So I got this whole description about outliers. So then one way to, yeah, so sorry, this Occam's razor, we want to try to usually have a trade-off between simplicity and the simplicity of a model and how well it fits the data. You know, we want the model to be relatively simple, but we want it to fit the data well. So it's kind of a trade-off. And often we use a validation set to try to tune these meta parameters. So we kind of usually we don't have access to the test set, but we can, whatever data we've given, we can split it up into we can use 80 or 90% of it for training and the other 10 or 20% for validation. And then when we, whatever the meta parameter is here, whether it's the number of training epochs or the number of hidden nodes or something else, we often see this pattern where the training error continues to go down, but the validation error goes down and then up again. So we try to use this to, the idea is if you choose parameters that perform what give you a good validation set error, they'll probably give you a good test set error as well. And once you've settled on your meta parameters, then you can retrain using the entire training set. So overfitting, and then this is one method of avoiding overfitting in deep neural networks is this dropout. That when you're training, for each mini batch, you randomly select certain nodes that are going to not be active for that mini batch. And then in the end, when you're testing, when you've fully trained the network and you're deploying it, you use all the nodes, but you multiply each node, you multiply each output by the same fraction as the number of nodes. So, you know, if during training you only keep 70% of the nodes, then in deployment you keep all the nodes, but you multiply the output of each node by 70%, so that on average the nodes coming into the activation coming into the next layer is preserved. Yeah, so this is just a very clever way of avoiding overfitting for neural networks, and it's been shown that it's like equivalent to like an implicit ensemble of different architectures. Is there any rule of thumb for choosing number of hidden layers? And so okay, the number of hidden layers, right? So there's a few questions here. So first of all, the number of hidden layers, well, we'll get on to this as we progress. So when we get to week 3, we'll talk about the limitations of 2-layer networks and 3-layer networks. And then week 4, we've described week 4B as like image processing, but if you have a look a lot of, we've got the convolutional networks, and then a lot of what's going on with this image processing is special tricks to be able to train deeper networks. So, you know, weight initialization and batch normalization and that sort of thing. So there's sort of this progression in the course that we talk about 2-layer linear networks, and then 2 layers, and then 3 layers, and then how to get up to deeper layers. And then the number of nodes. Again, a lot of this is sort of trial and error, although for small networks, this process of checking the validation error can give you some guidance about the number of hidden nodes. And I guess the dropout rate, the same thing, that usually people try with different dropout rates and check the validation error. And so so again, this is a sort of a general purpose picture. I'm not sure what the training error would happen, but with the dropout rate, you could try different dropout rates and measure the validation set error and try to get an idea what's best. And different layers. So with the convolutional neural networks, sometimes people use dropout sometimes they use it in the convolution layers and the fully connected layers, sometimes only in the fully connected layers. So if you have a deep network, you might only use dropout in the last few layers, or you might use it in the early layers. There's different kind of strategies. Eric's asking, a way to tell noise from outliers. Okay. Yeah, so with the 2-layer networks, we often use a function like this at the hidden layers, either this or this. And then, sorry, we use this at the output layer as well. So now you notice this thing with the output layer, actually this particular, that graph isn't very good. Let me see if I can find a better graph. This is a better, these graphs are actually a better graph of what this function really looks like. That's the sigmoid, this is the tan H. You'll notice it's flat at both ends and a steeper in the middle. So when you're training items that are correctly classified, the gradient becomes flat. But interestingly, so it tends to give emphasis to the items that are close to the boundary. That's where the gradient is steepest. And if there are items that are very badly misclassified, the gradient becomes flat again. So one of the consequences of using this kind of it's actually, I mean, it's kind of a combination of the transfer function and the loss function. But what tends to happen is if you had, let's say you had a 0 that's very far away from here, you know, it's very, very badly misclassified. Eventually the network may choose to ignore that item because the gradient there becomes quite flat. So some of these networks have a natural behavior where if something's really an outlier, it will learn to ignore it. Yeah, but it kind of depends on the activation function. With if you use cross entropy and the loss function, if you use cross entropy loss function, which we'll talk about tomorrow, then it's less likely to ignore those outliers. So sometimes the choice of the loss function depends on, in part, on how well you trust the data, whether you think there may be outliers there or not. The number of weight updates does depend on the data. Yeah, so often when we're training, we talk about an epoch. Usually one epoch it's not always done like this, but usually one epoch means one. If you present all of the training items once, that's called an epoch, and then you have to decide how many epochs to train for. Yeah, these are good questions. Yeah. Mohammed's asking about which activation function. Yeah, so far we've talked about sigmoid and hyperbolic tangent. So one of the techniques we're going to look at for trying to train deeper networks is this rectified linear unit. So it often, not always, but often these ReLUs tend to work better for, when you have a deep network. Good. Anything else? From week 1, activations is to simulate the neuron. Why do we use activations? Well, yeah, so I think so what would happen if we didn't have any activation functions? So let's forget about the one on the right and just look at the one on the left here. You have inputs, and then you have a linear function, and then you've got the first hidden layer, and then you got a linear function, you got the second hidden layer, and then you got the outputs. Now, I thought about including this as an exercise, but I don't think I did. But if let's suppose that you didn't have an activation function here, you just composed 3 linear functions. Well, it turns out that applying a linear function is the same as multiplying by a matrix, and then applying this next linear function would be the same as multiplying by a matrix. And so if you compose 2 linear functions, the result is also a linear function. So if you just had a linear function here and a linear function here, and you didn't have any activation function, these 2 layers would just be performing a linear function. So you could actually get rid of the 2 layers and replace it with 1 layer whose weights are the entries in the product of the 2 matrices. Yeah, so if you didn't have an activation function, you wouldn't get any extra benefit from having another layer, because the function would always be linear. So the purpose of the activation function is to give us a little bit of nonlinearity. You have a linear map, and then you have some nonlinearity with the activation function, and then you have another linear map, and then you have some more nonlinearity. So it's a way of including some nonlinearity into the model, but in a kind of controlled way. I think that's really the reason why we need the activation function. Now, when we get to language processing, we will see a model called word2vec, where there isn't any activation function, but there it's on purpose that the entire model is linear. So now the early, if you actually look at what happens in the brain, I think this early these activation functions were kind of meant to crudely model what happens in, I mean, the brain is much more complicated. You see actually networks often fire multiple times and then they become quiet, and then so there are these sort of models called spiking neurons which try to more closely model that, whereas here we're sort of, this number in some ways is modeling the spiking rate of a neuron. So it's a kind of, in a way, a crude approximation of what's going on in the brain. And then when we get to these more exotic functions like ReLUs, it's kind of getting further and further away from what actually happens in the brain. But it always serves this function I mentioned of something that's just, you know, a little bit non-linear kind of thing. MLP, yeah, so a multi-layer perceptron is a kind of neural network. It's just yeah, it's a little bit, so I guess technically, yeah, this terminology is a bit sort of you know, for historical reasons, I guess. So normally a perceptron means that you have a one-layer network and the output is not continuous. It's strictly either 0 or 1, and then you use the perceptron learning algorithm. Now, it is possible to have a one-layer neural network which computes a linear function, but often we just would, but then you have as like a sigmoid at the output, and then you train it by gradient descent. That's sometimes referred to as linear regression. And then people started using the term multi-layer perceptron technically for these situations where you have two layers, but at each layer you've got like a step function. But then sometimes when you get to this, when you replace this step function with this continuous activation function, sometimes that's when it really becomes a neural, well, they're all neural networks. I suppose neural network is just a general term, but some people still use the term multi-layer perceptron even in that situation, but it's just a kind of historical terminology. I mean, in this exercise here, the term multi-layer perceptron is certainly makes sense from the point of view of this exercise, because we're not doing gradient descent, we're just designing the thing by hand. When we get to gradient descent, it's better to just call it a neural network rather than a multi-layer perceptron, but sometimes people still use multi-layer perceptron in that situation. I hope that made sense. So where was I? Oh, yeah. So this is what we'll be looking at tomorrow. We'll be looking at the sum squared error and cross entropy, and how to, the mathematical origin of these things. And then we'll be looking at log softmax, and then weight decay, and the derivation of weight decay using Bayes' theorem, and momentum, and adaptive moments. So yeah, try to have a look at that. Try to have a look through this materials today or tomorrow morning, and we can discuss that tomorrow. Good. Any final questions? If not, I'll see you tomorrow.